Last time we looked at set equality, so now let's look at a somewhat weaker property, which is a subset. Okay, so here's our definition. We say that S is a subset of T, and this is the way we write it. Okay, that's our subset symbol. And S is a subset of T if every element of S is also an element of T. Okay, so that's the definition. And here's a simple example. Boy, that is the worst set brace I've ever written. So let's try that. Okay, so 1, 3, 5, for example, that is a set, and that is a subset of 1, 2, 3, 4, 5. And how come? Well, 1 is in the second set, right? 3 is an element of the first set, and sure enough, is an element of the second set. And 5 also is in the second set. So we simply have to do that. We look at each element of one set, and we show that it's also an element of the second set. That's the definition. Okay, at least that's what it is in English. Now, how can we translate that a little bit more into math so we can actually prove things? And here we have S is a subset of T if and only if this is the definition. For all x, x belongs to S implies that x belongs to T. And you see that that's really, really similar to our definition of equality. In fact, the only difference is right there where we have implies as opposed to if and only if, right? So that actually gives us kind of a beautiful way of looking at equality, right? So when we try to prove that two sets were equal, what we did was we had to prove an if and only if, and we broke that into the if part and the then part, okay? But now that we have kind of subsets in mind, we can also think of it this way. To prove that S is equal to T, the first thing we're going to do is prove that S is a subset of T. That's really the if part, right? Because as x belongs to S implies that x belongs to T. And then we're going to prove that T is a subset of S. That's the only if part. If x belongs to T, then it must belong to S, right? So that's kind of our approach for proving that two sets are equal. Okay. All right, so let's focus just on subset for the rest of this video, and we'll prove some kind of small theorems about subsets. So here's our first small theorem. The empty set is always a subset of any set, okay? Any set. So let's do the proof. First of all, let's get our theorem right. We said any set, so for all S, empty set is a subset of S. Okay, so how do we prove that? The same way we've proved things up to this point in the course. So we have a quantifier, so let's remove it, right? Empty set is a subset of S naught. That's just a quantifier removal, okay? And then here's a really important hint. Whenever we're doing a proof and it doesn't look like it's going anywhere, check to see if there's any definitions that you can open up. So how do I prove that something is a subset of something else? Gosh, I don't know. Well, we have a definition, right? And our definition is that for all x, x belongs to the first set, the empty set, implies that x belongs to the second set, S naught, okay? So we just do that, and we say, well, this is really what I'm trying to prove. Now, by the way, we go back to where we were up to this point. We have a for all, so let's remove it. It's already at the front. There's only one, so it just don't need to rename. Okay, so we'll replace x with the constant symbol x naught. So x naught belongs to the empty set, implies that x naught belongs to S naught. And now the proof kind of takes care of itself, because x naught belongs to the empty set. Wait a minute, the empty set is defined as the set that has no elements. So x naught can't belong to it. That means that that proposition is actually false, right? So false implies that x naught belongs to S naught. False implies anything, right? That's actually a propositional fact. So there it is, true, done. Okay, so that's kind of our first theorem having to do with subset, and you see that it's just a matter of opening up the definitions and just doing propositional or predicate reasoning. Okay, let's do another one. For any set, S is a subset of S. So every set is an element of itself. a subset of itself. Okay, so let's prove that. Again, we start by just giving the real theorem with the full quantifiers. For all S, S is a subset of S. We have quantifiers. They're already at the front. There's only one of them. No need to rename. So let's just remove it. S naught is a subset of S naught. Okay. What do I do now? Oh, I'm stuck. Open up the definitions. So our definition says that for all x, x belongs to S naught implies that x belongs to S naught. Okay, we made some progress. For all x's in the front, there's only one quantifier. There's no need to rename it. It's already been migrated. Remove it. x naught, that's our new constant symbol. X naught belongs to S naught implies that X naught belongs to S naught. Hey, that's convenient. That's just P implies P, so that's true. Again, we have here propositional reasoning. We have here predicate. Predicate logic reasoning. Okay, so this step here is kind of the only step that actually used sets. Okay, everything else is predicate propositional reasoning. That's why that first module in this class is so important. Okay, just a quick aside. S is always a subset of S, right? Okay, that's what we just showed. Not very interesting, right? So when I look at S as a subset of T, I may actually want to say something stronger, like S is a subset of T, and by the way, S is smaller than T, okay? So one thing that I might do is write it like this, okay? That shows that S can't be equal to T, okay? And incidentally, some people like to use this notation when they say subset to mean that it could be equality, right? So S is a subset of S, possibly being equal to S, right? S is not a subset of, S is a subset of T, but is not equal to T. So we emphasize that, okay? We call this a proper subset, okay? And by proper, what we mean is that it actually is a subset, right? And it can't be equal, okay? All right, let's see, let's prove another theorem about subsets. Let's prove that the subset is transitive. So we have three sets here, R, S, and T, okay? And what we're saying is that R is a subset of S is a subset of T, and we want that to then show that R should be a subset of T. So let's see. We start with, just as before, we just write down all the quantifiers that we're missing, right? So for all R, for all S, for all T, R is a subset of S and S is a subset of T implies that R is a subset of T, right? Remove the quantifiers. R naught is a subset of S naught. S naught is a subset of T naught implies R naught is a subset of T naught, right? We've done that a million times. And then we're stuck, so we'll open up the definitions. Oh, for all X, if X is a subset of R naught, then X is a subset of S naught, and so on, okay? Now at this point, I just went ahead and jumped to true, okay? So what I've done is I skipped a few steps. But let's talk about those steps that I skipped. I have three different quantifiers. They're all for all X. So the first thing I need to do is rename the quantifiers. So we have X, Y, and Z, for example. Okay. The next step is to migrate the quantifiers to the front. The big symbol that we have is an implication. So this quantifier will migrate as a for all. These ones are to the left of the implication. So those are going to migrate as there exists. Okay. Remember our strategy. This one will migrate first, and then these ones will migrate second. It doesn't matter what order those two go in because, you know. Now, okay, so I'm going to end up with for all X, for all Y, there exists a Y, there exists a Z. For all X, there's no choice. That's going to be X naught. Okay. For the other ones, I do have a choice, right? I can choose whatever I want for those quantifiers. Let's say there exists Y, there exists Z. I should choose X naught, right? Because that's the point that I need to prove something about. So I'll end up with X naught belongs to R naught implies X naught belongs to S naught. X naught belongs to S naught implies X naught belongs to T naught. And those two things must imply X naught belongs to R naught implies that X naught belongs to T naught. Okay. Actually, that's a very easy proof to do, right? It has the structure of P implies Q and Q implies R should imply that P implies R. That is purely a propositional statement. And so with just raw propositional reasoning, we'll be able to derive true. Okay. I skipped all the details because by this point in the course, I want you to start feeling very comfortable about both reasoning about predicates as well as reasoning about propositions. So that's just going to be true.